Where's Garrett?
Oh, there is Garrett, yeah. I already talked to him. He said that he would be here. Okay, so this is Math 265. Multivariable Calculus. It is November 4th.
Yeah.
See? Okay. I don't think that clock is right.
The minutes are.
Okay. Es las 12:05. Sorry. Is that bad? I want to practice, that's all. So today we're going to I can't do I can do this part too. But now I'm really losing what I can do. So we're going to integrate with spherical coordinates.
How do you pronounce that in Spanish?
What, spherical coordinates? I have no idea how to say that. Oh, I mean, I could
Integral.
integral.
I don't know, I'm just reading.
Coordenadas esféricas.
Coordinatas esféricas. Oh, that sounds about right, because you wouldn't start with you certainly can't say spherical in Spanish because they don't have that sound there. You need to esférico. Esféricas? Okay.
I think Jonathan should go to
Esféricas.
Yeah,
Gracias. All right, so we're going to see the formula for how to translate our normal triple integrals into one that uses spherical coordinates. And instead of going through the whole picture and the limit definition again, because you kind of know how that works now, I'll show you the formula. So let's assume that you have a spherical rectangle. So what do I mean by that?
Just do that.
You've been able to rewrite your region in terms of rho, theta, and phi, where each one of them sits between two numbers. So say rho goes between A and B, theta goes between alpha and beta, and phi sits between C and D. Okay, and we'll do an example to see how you might translate a rectangular region into one of these. But for now, you just need to know that you've done that step. And the question is, what does the triple integral, right, over E of f become? So, well, it should be an iterated integral. That much we know. And in fact, we'll just run it backwards here. C to D, alpha to beta, and A to B. So that means we're going to integrate with respect to rho first. Okay, so now we have to replace our function. I told you he'd be. So we started with a function of x, y, and z, but we need to transform the x, y, and z into the spherical coordinate system. All right. So last time we wrote down. That's very distracting that your hair is down. I'm not used to it at all. Last time we wrote down the transformation was how to convert your rectangular coordinates into the spherical coordinates. So the x became rho sine of theta cosine of phi. Is that right? Yeah? No, I got it backwards.
And when you not happy, I was like, what's wrong?
Sine of phi cosine of theta.
What? It's the other way around?
Okay, so this is what the x became. Okay, we're going to have to actually forget this stuff already. We ran out of room. Okay, what about the y? Well, the y is almost the same thing. It becomes rho sine of phi sine of theta. Is that right? Okay. And what does z become? Z should just be rho cosine of phi. So that we replaced all the x, y's, and z's in the function, right, by these transformations. Okay. And then we also know at the end that we're going to need to have, well, let's see, a d rho, a d theta, and a d phi. And they correspond here. The order here is right, corresponds to the order in which I wrote down the bounds. Wrote down the bounds. Right, so the CD was from the phi, right? Because the phi was between C and D. The alpha beta, that corresponded to the theta, and the AB, that corresponded to the rho. Okay, but I left some space up here, and why? Well, we know that when we translated our double integrals into polar coordinates, that there was a cost of doing business, right? We had to pick up an extra r. Well, there's a cost of doing business here for spherical coordinates, and it's a little bit worse. The cost of business is first, well, remember here, kind of the rho takes the place of r in this game. And instead of picking up an extra r, you pick up an extra rho, but actually you don't just pick up one extra rho, you pick up two. It's rho squared. But that's not all you pick up. You pick up a sine of phi. Now you might ask why. Why did these come in? Well, let me just reason by analogy. Before, when we computed what's going to happen when you change from regular coordinates to polar coordinates, as part of doing that, we had to compute the area of a sector, like this, right? Kind of part of a sector. Okay, so well, it should be lined up right. Okay, so we computed the area of that, and when we computed the area, remember it was something like a half r squared theta, or this angle here was theta. Okay, well at least this would have been the area of the entire thing. Okay, and then you had to subtract out, well, if this was say R1 and this is R2, right? How far away you are radius-wise, you had to do the R2 and then you had to subtract the R1. It was from this formula that we picked up the extra R. Well, that's where we got it from. When you compute, right, the limit that gives you this, you have to look at, well, we drew it yesterday, and I'll try to reproduce that again. Here. Okay, so somehow there's a spherical rectangle. And when you're computing the volume of this, I won't write it down, but that's where this term is coming from. Okay, in the same way we got an R by looking at this formula, we get an extra rho squared sine of phi when we compute the volume of something like this. I don't want to go into the details though. Okay, so this is this weird formula. So you get an extra rho squared sine phi. So this is a little hard to remember, right? Before you picked up an extra r when you did polar. Spherical, you got to remember you get an extra rho squared sine phi. Rho squared sine phi. Rho squared sine phi. Rho squared sine phi. Yeah. Okay, you got to say it a bunch of times, and then you just remember it. Rho squared sine phi. Rho squared sine phi. Okay. All right, so why don't we do an example? And this is an example that some of you might remember from 166, namely compute the volume of a sphere. So in 166, the way we did that is, well, perhaps we took a circle or maybe a semicircle, and then we rotated it around the x-axis, for instance, and then we used our ways of computing volumes of revolution. Yeah, okay. But it's also, we can compute it quite naturally with a triple integral. So how do we do that? Well, first I need to give you a sphere to compute the volume of. So let's take the easiest one we can think of. So the region is just going to be the area of the base times the height, which is always 1. So it's just the area of the base. So it gives you the area. So for a triple integral, you can find the volume by just integrating the function 1. Which we don't write. You should just write dv. Right? 1 times dv is dv. Okay, so fine. Leave it like that. So we could write this as a triple integral. And what's it going to look like? Well, the x goes from minus r to r, the y goes from minus square root of r squared minus x squared, and up to the square root of r squared minus x squared. And then you go minus square root of r squared minus x squared minus y squared, up to the square root of r squared minus x squared minus y squared. And then you go dx, and you go dy, and you go other way around, dz, and then dy, and then dx. Okay. Now, when I do this first one, I'll get a z, and I have to evaluate it at the endpoint and subtract, and so it's going to give me 2 of these. And then I'm going to have to integrate that with respect to y.
Tell me we're going to switch.
And Jenna says, let's switch. Okay, good. We agree. This is not a good way to go. Okay, fine. So let's rewrite E in spherical coordinates. So in spherical coordinates, let's see, what about the rho? All right, the rho is the distance from the origin to a point on the sphere. All right, or actually any point, because we're trying to do the volume, so we can get any point in between even. So the rho goes between 0 and 1. Right? What about theta? Well, let's see. Theta is what happens when you take some point anywhere in here and you project it onto the xy plane. And then you look at this line segment from the origin and then look at the angle that you get. Well, now a sphere, you get points going all the way around. So theta goes between 0 and 2 pi. And then the angle between these line segments and phi, and the z-axis, that's what you call phi. Let's see, that can go all the way from 0 to pi. Now, why don't we go more? Well, remember by assumption, we assume that our rho is always non-negative and that our phi goes between 0 and pi. If your angle was over here, right, you'd say, oh, well, now look, my phi's bigger. But no, you actually, right, over here the theta changes. Right? So the theta would be over here. That's what makes up the change. You actually just compute this angle. Right? That is from here to here. And that would be your phi, not the one that goes all the way around. So phi is going to go between 0 and pi. So that tells us another way to write this integral. Well, it's again as a triple integral, but now, okay, it looks like we do the phi's first. So the phi goes from 0 to pi. Then we'll do the thetas on the next one, and that's 0 to 2 pi. And then we do the rhos on the inside, and that's 0 to 1. Then we put the function, and we have to replace all the x, y's, and z's with the garbage. But what's our function? Function's just the constant function. There are no x, y's, and z's. So we don't have to replace it with anything. It's still just 1, right? Still 1. But, of course, there's a cost of doing business. When you go from rectangular to spherical, you pick up rho squared sine phi. Rho squared sine phi. Rho squared sine phi. Okay, so we'll forget the 1. We don't need it. Rho squared sine phi, and then we do d rho, d theta, d phi. Okay, so there's been a trade-off. The bounds are certainly much easier. The integrand is harder, or so it would seem. Okay. But let's give it a shot, see what we can do. So we're first integrating with respect to rho. So the sine of phi is irrelevant. You can pull that out. This is 0 to pi, 0 to 2 pi. In fact, the sine of phi is going to be irrelevant until we get to the d phi. So I can actually pull that all the way out to the last integral. I can put a sine of phi here. And then integral 0 to 2 pi, integral 0 to 1, rho squared, d rho, d theta, d phi. Okay. So when I integrate rho squared, I get 1/3 rho cubed. Ah, that's really good. 1/3 rho cubed. That has to be really good. By the way, the r here, that really will become our rho in the final analysis, right? The rho is going to be out here, but in any case. Oh, actually, here's where it's going to matter. We wrote 0 to 1 because we were thinking of a sphere with radius 1, but it actually should be r, right? In our general case, where we have a radius r sphere. So this, that should be an r, and that should be an r. Okay, so when we integrate, though, we get 1/3 rho cubed evaluated at 0 and r, d theta, d phi. But you can already see where we're going to get a 1/3 r cubed out. So this is very good. 0 to pi sine phi, 0 to 2 pi. And actually, I can pull this 1/3 all the way out. It's just a constant. And here I get 1/3 r cubed, and when I plug in 0, I get nothing. So just r cubed. D theta, d phi. Now this r cubed is a constant, actually. Right? None of these things are going to see it, so I can actually pull that all the way out. So I can rewrite this as 1/3 r cubed, 0 to pi. Oh, forgot my sign. I'm Capricorn. And then 0 to 2 pi, d theta, d phi. Okay. Well, here I'm just integrating 1 from 0 to 2 pi. So it's just the length of the interval. It's just 2 pi. So I can pull a 2 pi out, and that'll give me 2 pi over 3 r cubed, integral from 0 to pi sine of phi d phi. And we'll see, when I integrate sine of phi, I get negative cosine of phi. So let's see, 2 pi over 3 r cubed, negative cosine of phi, and then phi goes from 0 to pi. Okay? So when I plug in pi, cosine of pi is -1, but then there's another negative out here, so it becomes +1. And then I subtract what happens at 0. Cosine of 0 is 1, but I can do -1, so minus minus 1 is 1, so 1 plus 1 is what I get from this. Yeah, the first one was, so I get minus 1, minus 1. Pi over 3 r cubed, okay, minus 1, minus minus 1 minus minus 1, which is 1 plus 1 is 2. 2 times 2 pi over 3 is 4 pi over 3 r cubed. 4/3 pi r cubed. Sure enough, your 5th grade teacher was correct. You don't have to go back and egg her house or something. And you can see that, well, I want to redo this calculation again, just to show you something that I was trying to show you yesterday, but it didn't quite work out. But you see, this is much easier to do than this was going to be. Even though the integrand up here was very easy, it was just a 1. But you had all these limits in here that were really nasty. Let me just quickly redo this integral derivation. And the reason why I want to do it is because I want to show you this product rule in action. Let's rewrite this here. So we had, is it 0 to pi, 0 to 2 pi, 0 to r, and then it's rho squared sine of phi, d rho, d theta, d phi. No, it's okay.
Can you just explain again why theta goes from 0 to 2 pi and phi goes from 0 to pi?
Yeah, so the theta is, okay, what angle you can get if you go in the, you project to the xy plane, and then you look and see what angles you get.
Okay.
Okay, and if you just project down, you get a circle.
Oh, okay.
Okay, and so it can go anywhere around the circle, so that's 0 to 2 pi. Now, what about the phi? Well, the way that we write down our polar coordinates is we make, our spherical coordinates, we make the assumption that the rho is always non-negative. Assume rho greater than or equal to 0. Bless you. And that the phi is between 0 and pi. That was an assumption we made at the beginning. So if you had one where you'd say, this should have some phi greater than pi, that tells you don't compute phi that way. Compute phi by going from this line segment to the z-axis in that direction.
Okay.
Or in this direction. Either way. Same sort of angle. So you just compute it this way.
Okay. So we just knew that assumption?
Yeah, that was just an assumption we made when we wrote down the spherical coordinate system.
Well, think of phi if phi is a constant, it's not a variable. Think of it as making it a cone around the z-axis. Like if you have a specific phi and a specific rho, it would make a cone around it. That's the way I remember it.
Wait, what?
Like say that your rho and phi are constant numbers, okay? They're not variables. And and the theta can go all the way around from 0 to 2 pi, it would make a cone. That's how I remember it.
If you took the line segment, and then rotated. So I think what Ben is saying that if you fixed a point somewhere out here, all right, you have a rho, you have a phi, and even at the beginning you have a theta. All right? And then take this line segment, and now take this line segment and allow theta to change. So theta can go from 0 to 2 pi, so it goes like this.
Okay.
When you do that, what shape does that make? And it makes a cone. Because you have this nice slanted line, and then you rotate it in a circle. Ben is saying this helps him remember.
The phi can only go from 0 to pi.
I don't see why that helps you remember that.
Because once you get halfway down, once you get your phi down to the xy plane, you're only at phi equals pi over 2.
It is true, okay. Phi would be pi over 2 here, and you can make it go down to pi.
Yeah, and that's it, you're done. You don't have any more values that you can put in for phi.
We'll have to figure this out, what you're meaning later. I'm not exactly sure what you're saying, so I mean, I understand what you're saying. I just don't, I'm not following how it's connecting to the question, but we'll figure that out. All right. So this is a function that is broken up into the different variables, right? You have a rho squared, that's a function of rho. You have a sine of phi, that's a function of phi. There's no connection between the two. So this is where we can use that product rule, right? Because there's nothing up here in the, none of the limits of integration depend on any of these variables. So we can rewrite this as the integral from 0 to pi of sine of phi d phi. That's the d phi one. We can then multiply this by the integral from 0 to 2 pi d theta, because there are no thetas. And then you can write as the integral 0 to r of rho squared d rho. And this will make, I think, computing the integral a little bit faster. Right? Less likely to make some errors. Because now you can just say, this is, well, that's the minus cosine of phi, which we evaluated pi at 0. And so this is what you get a 2 from. This is just the length of the interval, so it's 2 pi. And this is the 1/3 rho cubed. Evaluated at r, and 0 gives you a third r cubed. Okay. And so then the product is 4/3 pi r cubed. So it's handy to use this formula to compute these things. Okay, so this is nice. You can compute the volume of a sphere.
What happens when it's not a sphere?
What happens if it's not a sphere?
Well, I'm just asking, because here we're just integrating 1. So if it wasn't 1, would you use the x squared, y squared, z squared to figure out how to convert those? You know what I mean?
So you're saying let's do an example where it's not so easy.
Yeah,
Okay.
sure.
Fine. Fair enough.
What do you guys? Oh, yeah, what a long thing that we wrote. Like it said that if we-
So the nice thing is, if you're using triple integrals to find volumes, the function is always 1. So if you're just trying to find a volume, then the function is 1. But if you're actually trying to compute the triple integral of a non-1 function, right, then of course you have to use this nastier formula. So let me, let's keep the region basically the same. I guess last time I wrote equals to r squared, but that was wrong. And why was that wrong? Well, if I wrote equals r squared, I mean I did write it, it means that I'm actually just taking the outside, right? The sphere itself. But if I want the volume, I need really everything on the inside. So it should be less than or equal to r squared. So let me use here a region which is, it's just going to be a sphere, but I'm going to integrate over the interior of the sphere too, so I'll let it be less than or equal to 1. So this will be a sphere of radius 1, and I'm integrating over the whole region. Think of it really as a ball. It's not a hollow ball, it's like a bowling ball. It's really filled in, heavy. It's not a tennis ball, where it's just filled with air. So this is, again, okay, it looks like it's been squashed, but I really want everything inside of it. Okay, and what am I going to integrate? Well, I'm not going to integrate 1 this time. I'm going to integrate e to the x squared plus y squared plus z squared to the 3/2 power. This will put hair on your chest. No, not you, Karen.
No, my question is, will the formula that we're integrating over always be given, or do we have to figure it out like on the other one? We just figured out that.
Well, the way we figured out on the other one that was 1 is because we were asking what is the volume. Right? That's very specific. If I asked you for the area, then you were using a double integral, then you'd still use 1. Volume with a triple integral, you use 1. Right? But otherwise, remember, this is no longer computing the volume of something. It's more like it's the hypervolume. It's like a 4-dimensional volume of something. But it's not the volume of anything in 3 space. It's computing other things, but that's not one of them. So here I have to give you a function to integrate. Okay. Well, let's see. Again, the limits of integration are going to be very much like it was last time. Okay, r gets replaced with 1. But the limits would be exactly the same. But now the function would be not 1, but e to the x squared plus y squared plus z squared to the 3/2 power. And this already is looking quite bad, and we don't want to do it. And so Jenna says,
Change the x, y, and z.
yeah, good idea, right? We'll change the coordinate systems. Okay, fine. So if we want to write this in spherical coordinates, right, well, we already know what the bounds are going to be. We copy what we did before. Okay, because it's a spherical, e is really easy to write down. So 0 to pi, 0 to 2 pi, 0 to r is 1. Okay, so that part's going to be easy. 0 to pi, 0 to 2 pi, right? We're just redoing what we did last time, only now radius 1 circle. Now we need to actually fiddle with the function. We get an e, and then we raise it to, well, we have x squared, y squared, and z squared, but we're supposed to be switching this into polar or spherical coordinates. So we need to replace the x, the y, and the z. So what is x? X is rho sine of phi cosine of theta. Is that right? It should be written down in your notes.
Yeah.
Take a peek. So then I need to square it. So it becomes rho squared sine squared phi cosine squared theta plus, then I have to do the same thing with y. And y,
That's just x.
let's see, is rho squared sine squared phi sine squared theta. And then I need to do the same thing with z. Now z is what? It's rho cosine of phi. Is that right?
Yeah.
Rho cosine phi. Okay, so when it's squared, it becomes rho cosine squared phi. And then you have to raise it to the 3/2 power. Okay. Are we done? Yeah, right? It's the cost of doing business. You pick up a rho squared sine phi, and then, okay, let's see, 0 to 1, that was our d rho. 0 to 2 pi, that's our d theta. 0 to 2 pi, pi is d phi. Whew! I'm telling you, it's the sort of thing, if you do this at home, you put up a whiteboard in your room and just start writing this stuff down, your parents are going to think you're a genius. They're going to bring their friends over for coffee and say, come into my room and just look at what she's doing. Now, if your parents say, look at what she's doing, Taiwei, I apologize. That's not what they're supposed to say. Okay. Do you see anything that will help us here? Because this looks pretty bad. I mean, this certainly looks worse than what we were even going to get here. Whenever you see sine squareds and cosine squareds living together, you should smile.
Because they could get 1.
All right. Let's see. Look, you have a rho squared sine squared and a rho squared sine squared. So you can factor that out. And when you what are you left with? Cosine squared plus sine squared, which is 1. Okay. So this whole bit right here is just rho squared sine squared.
And then you could do the other one. Here, get it.
Yeah, look at that then. You have rho squared sine squared plus rho squared cosine squared. Factor out a rho squared. And you just get sine squared plus cosine squared, which is 1. So actually this entire exponent is now rho squared. to the 3/2 power. So, let's see, this is 0 to pi, 0 to 2 pi, 0 to 1, e to the rho squared to the 3/2. Okay, that's 2's cancel, you get rho cubed. And then you have rho squared sine of phi d rho d theta d phi. Now this looks a lot better. If we use the product rule, right, which we can do because the phis and the rhos and the phis are separated, I can write this as the integral from, let's see, 0 to pi sine of phi d phi, and then 0 to 2 pi d theta, so there's no thetas in here, and then 0 to 1 rho squared e to the rho cubed d rho. Okay, now let's see. I feel like we've computed this one before. That always turns out to be 2. So that's minus, okay, the integral's minus cosine, then we evaluated the endpoint, and we've done that a couple times. There. Okay. So this one is 2. This one is the length of the interval. It's still 2 pi. We've computed that before. Okay, so the only interesting one is here. How would we do that? Rho squared e to the rho cubed.
Can we use the tabular?
What's that? We don't need to use the tabular method. Much easier. Use substitution. Right? Let u equal rho cubed. When you do that, then du is 3 rho squared. Okay, so you're just missing a third, and that's, you have to add in an extra third, but then it'll just be e to the u, which when you integrate is e to the u or e to the rho cubed. So this is a third e to the rho cubed evaluated at 0 and 1. And let's see, when you evaluate it at 1, you get e to the rho cubed. I mean e to the 1 cubed, which is just e. And when you evaluate at 0, you get 1. So let's see, you have 4/3 pi. Right, that's what all that's coming from, and then e minus 1. Not bad. After you do a little bit of trigonometry, this became a very easy integral. Okay. So, yeah, we're out of time. I just say, just one last thing. You're going to get a lot of practice doing this. The question is in the future, when do you know, how do you know whether to use cylindrical coordinates or spherical coordinates? What's better? Spherical coordinates is usually really good when your surface is a circle or a sphere, something circular or maybe a cone. Cylindrical coordinates is really good for things where there's symmetry around the axis. Right? Now, there's a lot of overlap in those cases. In fact, you could have done a lot of the stuff we've done with both examples with both methods. All right? So you can try either, whichever one you're liking. Usually I like cylindrical first just because it's a little faster and easier. But they both will work. Okay. So start working on the homework. And tomorrow we're going to shift gears and talk about cross product of vectors.